In this video, we're going to look at analyzing the mathematical properties of the selection sort algorithm. All right, so I have my code on the top right. So this is kind of stuff we talked about before. This is my standard algorithm. And I want to basically have a better sense for how does it behave? How does it behave when I give it data? How much work does it need to do? So I have two questions here, and these are very typical questions. These are the ones we're going to ask in most sorting algorithms. For comparisons, how many? Exchanges, how many? All right, so we got to figure this out. So let's look at the code, and I'm going to do this. I'm going to just do this. Well, I'll do this for you guys, but eventually you should be able to do this yourselves, right? When you look at an algorithm, you should be able to answer these questions. How many times does this function run? So let me see. I'm going to go look, and I'm going to try to do compares first. So I want to know for a given input of size n, how many comparisons will be required? Well, what I'm going to do is basically look for where do compares occur. Well, it's over there. Excuse me. It's not over there. It's over here. So I have basically that call to less. Less is a function that we give it two elements, and it tells us, hey, are these two things in order, right? Does this one belong before this other one? So that's the comparisons. Now I want to know how many times it happens. And this is actually going to be a little bit tricky. It's going to be actually harder than exchanges. We'll do exchanges later. We'll do it in a minute. But comparisons is a little bit of work. So a couple observations here. First of all, I want to look at it with respect to loops. If I look at it, I notice it's inside of two loops. So I have a loop here and a loop here. And I've written the letter n there basically to say, how much work is it going to do? Like that outer loop, it's running some fraction of n, right? The inner loop is also running some fraction of n. So that gives you kind of an idea of how many times it could potentially run. So maybe if this thing basically ran every single loop iteration, if it ran every single time both those loops ran, it would run n squared number of times. So I'll actually start by writing that over here, n squared. Now note though that this isn't going to actually happen n squared times. Now so the outer loop for sure, right, is going to run n times because it goes from 0 to n, right? So n. That's fine. That's great. But then notice things get tricky over here because in that inner loop, we start at I plus 1 and then go to n. So even though our endpoint is something that's familiar, it's an n variable, it's like, oh, it's, it's good. We're starting at a different place each time. This is where it gets tricky. So let's look over on the right-hand side. So on the right-hand side, we have another trace of running this algorithm on an input sort example. So basically, the entries in black, right, are the things that are unsorted. It's the things I need to look at, right, to figure out, what is the smallest thing. Gray is the region of stuff that I've already, examined. I pull the smallest one forward. I'm good to go. And so you can kind of imagine, right, it's like that I variable. As I number increases, I have less and less and less to search. So over here, looking at my chart, what I can see is, hey, this thing, maybe takes, has to compare n things over there. Then n minus 1, n minus 2, n minus 3, right? It's doing a little bit less work each time. So this is a little tricky to analyze. But what happens here, right, is that we can kind of realize that this, trace here, right, this trace, right, is basically a rectangle, right, or a square, because it's representing the fact that I have two loops running. So I have kind of my outer loop running, right? So this is my outer loop here. This runs n times, and I have my inner loop here, right, which also runs n times because they're both on the length of the array. What I see emerge is though a triangle, right? So I have basically this triangle of every time I do a little less work, little less work, little less work. It's basically 1/2 of n squared, okay? And this is a very common thing you'll see. And so the actual analysis here is to say that this runs n squared over 2 number of times. And if you want, right, you can do this other ways as well, right? This to me is a visual way of, okay, I have a chart here that shows me, I would have made this, right, if I was doing this from scratch on an algorithm. I would have some idea of, what it's going to do, right, the different operations. And here I can see, it's only doing this much work. It's 1/2 of, this square, so it's n squared over 2. That's one way to do it, right? Another way to do it was maybe to plug it into some sort of summation formula, right, and get out an answer that way. Same thing, right? You'll get the same answer back. But yeah, that's what we have, right? So n squared over 2, that's the number of comparisons this thing requires. And also note, right, it doesn't really matter what the input is. I'm kind of spoiling the last question here on the slide, but I guess it's okay. This algorithm doesn't really contain any logic that depends on what the data looks like. It's basically just going to do its stuff no matter what. So yeah, this n squared over 2 is basically going to be always the same. All right, so exchanges. What about exchanges? So exchanges is me going over here and wanting to analyze this thing over here, exchange. So if I'm looking at that, well, what should I do? Well, I want to count up how many times it's going to run. Well, let's see. Maybe I simplify stuff. So this stuff over here really has nothing to do with that exchange. So I will X that out. And basically what I get is I get a loop that goes from 0 to n and does exchange each time. Pretty easy. N. Okay, so that's what I get. So I have basically n squared over 2 for compares, n for the number of exchanges. So this is my algorithm analysis. This is how much work my algorithm will do on basically any input of size n. So this is how selection sort works. We're going to basically use this as a baseline, right, and try to have other algorithms that maybe require a little bit less. Maybe something like n log n. That would be ideal. All right, so take a look at this stuff. Make sure you have some sense of how we got to these two different values.